James Webb Space Telescope is impressive. It's 3 stories tall, as wide as a tennis court. It's got a 21-foot primary mirror. And then it's got these 4 instruments that are just incredibly powerful. It's the largest, most technologically challenging space telescope ever created. It's 100 times more powerful than the Hubble Space Telescope, but at half the weight. It's designed to look back in time, even further than Hubble, to see the very first galaxies to form after the Big Bang. Building Webb is truly a feat of innovative engineering. Each material must survive the turmoil of a launch and the varying temperatures of space. And it all starts with the elements. This is the James Webb Space. There's a lot of hustle and bustle because the integration is in full process. Just look at NASA's James Webb Space Telescope. Its gold mirrors are definitely its most stunning feature. And yeah, that's real gold.
Humans have a long history of searching for gold and using it in their most prized possessions. These mirrors weren't gilded to make them pretty. There isn't even all that much gold, about 5 men's wedding rings worth over the 18 mirrors. So I wanted to see for myself, why does it make sense to use a microscopic layer of gold on these mirrors? So our everyday mirrors tend to use silver or aluminum as their reflective material. One of the major differences between our earthly mirrors and these fancy optical mirrors is the position of the reflective material. Look at the side of this small mirror. It has the glass in the front and the metal coating behind it. That glass actually traps a tiny amount of light and creates what we call a ghosting effect. So the clearest reflection that we can actually have has the metal coating on the front. Dentists and hygienists also use front surface mirrors to get an accurate look at your teeth. The position of the reflective coating might make a sharp observation, but the kind of metal also matters too. There are a couple of reflective materials that really excel at reflecting infrared light, which is how Webb will observe. Aluminum reflects 85% of that wavelength of light, silver up to 95%, and gold up to 99% of all the infrared light that it encounters.
But gold is special, and I can show you using the rings that I typically wear. This one is gold, and this one is made out of silver. And in the presence of the right chemicals, these 2 materials react differently. I think actually it's a little easier to show kind of all of this with this spoon. My mom surprised me by pulling out this whole tub of silver. Not tub, it came out of a box. So I'm able to demonstrate sort of on a bigger surface here how silver can react differently using an egg. Smush that in. Get nothing. We've got nothing. So what we have is a really fast reaction between the sulfur in the egg and the silver, and it creates a new thin layer on the spoon of silver sulfide.
Silver might be great at reflecting infrared light, but it tarnishes so easily. Not only does gold reflect more infrared light, but it is also one of the most unreactive metals. It is too durable to oxidize and decay in space, and it is certainly Webb's best chance at seeing the cosmos.
I'm gonna go this way where it looks like there's probably a gold sink, which would just be in a pool like this.
I am on a quest for gold. Since NASA's James Webb Space Telescope has a microscopic layer on the mirrors, I want to know, where does gold really come from? Now, California is known for gold. It flows through the rivers, is embedded in the mountains. But is this really where gold originates? I know. This is a terrible example of what gold panning looks like. But at this point, I had already driven all the way to the San Gabriel Mountains, only to find that it is illegal to pan for gold because it is now a national monument. But it would just be our luck that we ran into Bill Schuster, whose family owns property for a really long time in the mountains, and he really showed me how to properly pan for gold.
See, the first thing you gotta know, you're gonna get wet, so don't worry about getting wet. Gold is so heavy, the ripples will catch it. Most people are so scared that they're gonna lose gold, and believe me, it will not go out. I already see two pieces, two big pieces in more angle. There you go.
So gold is incredibly rare. We can take all of the gold that we've ever mined or panned and stick it in 3 Olympic-sized pools. And the reason that gold is so rare is because it isn't even from Earth. It is extraterrestrial.
As it turns out, finding gold's cosmic origins is a topic of hot debate. So I needed an expert to help me understand, and luckily, Mansi was in the area.
Do you like to wear gold?
Yeah, in fact, I actually got this gold ring in India myself.
Gold is one of the heaviest elements in the periodic table. In fact, if you peeked into its nucleus, it would be filled with 197 neutrons and protons. And until a few years ago, we had no idea where gold is made in the universe.
Scientists debated what energetic event could make heavy elements. Is the power of a supernova enough? Or does it need more?
That turns out to be very difficult to synthesize in any ordinary cosmic explosion. You need a very special explosion that can actually synthesize heavy elements like gold by our process.
Now, the R process is one of the ways to make heavy elements like gold. It is another way to say rapid neutron capture process, and it happens in the matter of a couple of seconds.
On August 17th, 2017, when the 2 neutron stars merged, that's when we saw the hallmark infrared signature for the very first time.
Now, this neutron star merger was and is still a big deal. It's the only time scientists have witnessed and measured the R process in action. And up until then, it was all theoretical.
Let's begin with 2 neutron stars spiraling towards each other and then merging to give birth to a black hole. This is where we think we saw for the very first time the gold being synthesized. You have an abundant supply of free neutrons. So when these neutrons are flying out, they are able to bind to each other, join together, and undergo rapid capture. And this rapid capture gives you a slew of heavy elements all the way up to gold.
What I learned is that, like all heavy elements on Earth, gold has been here since Earth was formed. It was floating around in the gas and dust that formed our sun and all the planets in our solar system. But gold is heavy. Much of what we find comes up through many veins running through our crust. That's why we often find gold alongside rivers and volcanoes. But what is even more poetic, we're using an element forged in the death of stars to investigate the dawn of our universe. When you look at NASA's James Webb Space Telescope, you can't help but see the huge gold mirrors. But that gold is really only on the surface. The rest of the mirrors are made out of a metal called beryllium. Let's head over to the shop that worked on these mirrors to get a better idea about why this metal is so remarkable.
And it's like, follow the noises. Engineers chose beryllium for 3 major reasons. It is super lightweight. It is the second lightest of all the metals and only 2/3 the weight of aluminum. It's super strong. Beryllium is 6 times stiffer than steel.
Each of these cantilevered weights are the same except for the type of metal. They are the same length, the same weight, and size. Look at what happens when they are lifted and released at the same time. That beryllium wiggles with less intensity and stops moving first. That's because it's far stiffer than the other two.
So it can also hold its shape over a really broad range of temperatures, and that's especially important in the cold ones.
I measured these identical aluminum and beryllium mirrors, and then left them in some dry ice for a while.
Science.
I do have to admit that my measuring technique could use a little work, but the aluminum shrunk more than the beryllium. Materials as a whole tend to change in shape, volume, and density in response to temperature. When something is heated up, the molecules begin to vibrate and separate a little. The amount that the material changes is predictable and is based on its coefficient of thermal expansion. So beryllium, it stops shrinking and changing its size when it cools below 100 Kelvin. So the mirrors we see are a little too large on Earth, and will be the exact size they need to be once they are out in space.
Beryllium is obviously an incredible material, but everything does have its nuances. So, why isn't beryllium used more often?
Machining beryllium requires extreme care. If you think about it, beryllium actually is a powder that is pressed together and requires very, very light cuts. Any small mistake, it would crack, and there'd probably be a piece that would chip off. And you've lost a part that could be worth anywhere between $1,800 to $2,000 a pound.
Under the wrong circumstances, beryllium may be fragile, and it's fairly expensive. But it holds its shape well, is very stiff, and most importantly, it's lightweight. Rockets need a lot of fuel for each pound of payload. So any weight-saving measures are really, really worth it.
This is it. I am standing at the place where the beryllium was mined for the James Webb Space Telescope.
Let's take a step back. I traveled just south of Salt Lake City to a town called Delta, Utah.
Well, here we are. What is it? 5:30 in the morning.
And then back on the road the next morning as the sun rose up to meet the beryllium miners, all in my quest to find out. So Utah is home to many valuable materials: copper, magnesium, uranium, gold, and silver. But most of the world's beryllium is mined here. And engineers chose beryllium for Webb's mirrors because it is lightweight, it is strong, and it is dimensionally stable. So that means that it is not going to warp when operating at really, really cold temperatures. What is even here? As we were driving down into the pit, I learned that we were in fact driving on the beryllium.
This rock looks nothing like metal. Where is the beryllium? How does this turn into this?
I, of course, needed to speak to an expert, and he came in the form of the VP of Operations, Greg Gregory.
So we're actually standing right on top of the beryllium ore seam. Beryllium is in a volcanic ash dust. It was hydrothermally deposited millions of years ago and then covered by volcanic rock. We have to remove the volcanic rock on top of the ore seam, and then we use a scraper and a bulldozer to extract the ore that we're standing on top of. 90% of the beryllium that was mined in the world last year came from this deposit.
Let me clue you into how rare this metal is. This area has most of the world's known beryllium, but the highest concentration is only through a 10-foot tall diagonal ribbon well below the surface of the ground.
The ore concentration is 0.25% beryllium. So that means that in a ton of ore, there's about 5 pounds of beryllium. So to get to this point, we had to remove 400 feet of rock to get to the ore seam.
Once the ore is extracted, it goes through a bunch of processing to extract the pure beryllium. Then the powder beryllium is pressed into a block, ready for machining. Webb's mirrors started out as solid 5-foot tall, 5-foot wide, and 2-inch thick blocks of beryllium. But in order to machine those blocks, millions of pounds of rock were removed. It comes to about 4 tons of rock for every pound of beryllium. That is a lot of work for one remarkable metal. Beryllium is one of the many elements that people mine, and that's how we obtained it for NASA's James Webb Space Telescope. It exists in many rocks, just in tiny quantities. We collected rocks with the highest amounts of beryllium, crushed them up, put them through many chemical processes, and these rocks only have 0.25% beryllium. To explain beryllium's rare beginnings, we need to talk about the cosmic origins of most elements.
When a massive star is forming, it's mostly 2 elements, hydrogen and some helium. Over time and pressure, temperature builds up in the core, so much that some of the hydrogen atoms fuse, creating helium and officially bringing the star to life. That fusion creates a tremendous amount of energy and is literally what fuels the star and makes the light we see. That star will eventually run out of hydrogen, and the helium atoms start to fuse, creating even larger atoms. That keeps happening, and we get larger and larger elements. These new elements are denser than the former hydrogen and helium, and they cause the star to contract and get even hotter. But that all stops with iron. There isn't enough energy to fuse something more substantial, so once there's too much iron in a star, which means that there's no fuel, it dies, but not without a dramatic exit. The core collapses under the pressure, and all of the atoms knock around into one another, which causes a sort of shockwave, and it explodes into a supernova. This is the energy needed to create heavier elements. This is when more than half of the elements in the periodic table are made. But beryllium is not in that mix. Look at where it is on the table. It has an atomic mass of 4, much smaller than the heavy new elements. So why isn't beryllium made when the other small elements were? It's just too unstable. If, during the chaos of a supernova, a cosmic ray hits one of these newly formed larger elements, a special reaction happens. This is called cosmic ray spallation. This ray hits a molecule and it bursts into smaller particles. The pieces can continue splitting into smaller parts, some of which turn into beryllium.
It takes a supernova and a cosmic ray to reduce a large element into what could be a variety of combinations and sizes to create beryllium. No wonder it's so rare.
So in the heat of the summer, these visors really can make a difference. And the Webb telescope uses the same principle to block the heat of the sun and even what bounces off the Earth and the moon. And just like my car's visor, the telescope's sunshield unfolds, but its 5 layers are a little bit thinner.
This thin material is called kapton, and it makes the sunshield of NASA's James Webb Space Telescope. So what is this strange kapton? It's a combination of carbon, nitrogen, oxygen, and hydrogen, but its primary element is carbon. It is only 1/1000th of an inch thick. That's a quarter of the thickness of the thinnest hair you can find. The 5 layers of this reflective material will keep Webb cool. It'll block the light of the Earth and Moon and our very bright sun. Each layer is the size of a tennis court. The sunshield happens to be one of the most complicated parts of this telescope. And that's because it has to be packed perfectly like a parachute to fit into the rocket, and then it has to unfold in space. Let's get a better idea of how good this kapton is at reflecting heat. I asked our resident expert in all things MIDI to make me a 3-layered model of the sunshield using the same Kapton that's on Webb. And then we put this tiny light bulb to mimic the heat source that would be the sun, earth, or moon. See? You can see the heat reflecting off the bottom layer. And then the Kapton worked so well that none of the heat is detected at the top of the model. The sunshield is capable of dissipating 500 degrees Fahrenheit over the 5 layers, and that heat radiates out from each of the layers. That's why each layer gets a little smaller from the bottom to the top. NASA actually uses Kapton for most of its missions. It not only shields or contains heat, it also because it is electrically conductive. All that shifting Kapton of the unfolding sunshield, it could create static electricity. But that charge won't build up on the Kapton and jump to the observatory's super sensitive electronics. And then Kapton stability over a wide range of temperatures is why it's also a great choice. This modified version, called Mylar, might even help you if you get cold.
What is the backbone of life? That super stable central element to all organic molecules, and happens to be the 4th most abundant element in the universe? It's carbon. Carbon has once again proven its worth in the form of the Webb telescope backplane. Now this structure holds 2.5 tons of science instruments, those beautiful gold mirrors, and it's made out of a carbon composite.
You might be more familiar with graphite, a crystalline form of carbon. Graphite is really everywhere. It's in airplanes, bikes, our tripods. It's great because it's strong and super lightweight, just like Webb's backbone. Just look at the difference in weight between the aluminum and the same amount of the backplane material.
The backplane isn't entirely all carbon. A durable polymer binds those carbon fibers together with plasticated-like glue, and then they are baked in an autoclave like this. All right, so I think we should probably go just maybe in front of the Pathfinder. Once out in the cold vacuum of space, this backplane will shift, because all materials change with temperature. But this structure is aligned so that it's perfect once it does shift into space and cool down. That happens to only be 1/10,000th the diameter of a hair. So, frickin' cool.
Not every element that we use on NASA's James Webb Space Telescope is unique to the mission. Sometimes we use things that are tried and true and very abundant. We don't find silicon like this on Earth. It's pure form. It's usually paired with oxygen in the form of a silicate, and silicates make up 90% of the Earth's crust.
Between 2010 and 2018, people purified 7.37 million metric tons of silicon. 2018's global revenue was $11.4 billion. What makes this element so special that the epicenter of the tech world is named after it? Let's head over to the shop and see why silicon works so well for this mission. So yeah, silicon is cheap and available, but the reason we want to use it is because it happens to be a semiconductor. Now, a semiconductor is something that doesn't conduct very well, like this metal object, or insulate things, like wood would do. We want it to be able to do both with a little coaxing of electricity. A photodetector looks a lot like this, and it's on a silicon wafer. And we use it because it has a stable atomic structure. When light passes on this, the silicon lets out a few electrons. That is the electrical voltage, which then translates into data for the scientists. Silicon isn't the only semiconductor or even the best semiconductor. But its ability to switch between giving an electrical signal or not, meaning a 1 or a 0, makes it worth it.
Welcome to my kitchen. Today I'm going to attempt to make something that is really vital for the Webb telescope's ability to see. So let's give it a go. But first I have to make some distilled water. You see that? All right, cool. Let's get it done in the kitchen. It's a salt crystal.
Who doesn't love salt? It has a long and important history. Since it was once the only way to preserve food, it also dictated trade routes. It was one of the most coveted and expensive minerals. Today, we rely heavily on salt to keep our roads safe, and salty snacks are the best.
Webb needs salt. Not this tasty kind, but as a lens. So there are different types of lenses. Mirrors are a reflective lens that bend the light. And then there are transmissive lenses that allow light to pass through them. Here's the kicker. Visible light, it behaves differently than infrared light. So glass absorbs infrared light, but salt doesn't. The type of salt in here is sodium chloride, or NaCl, and even though it's the most common type of salt on Earth, it is not the only kind.
Salts are more than something you sprinkle on your food. A salt is a combination of two things: a positively charged element, usually a metal, from groups 1 or 2, and a negatively charged halide, usually from groups 16 or 17. They get their charge by either gaining or losing a negatively charged electron. So Webb uses 3 kinds of salt lenses: lithium fluoride, barium fluoride, and zinc selenide.
So making these lenses happens to be pretty tricky. I've been growing this one now for about 3 weeks, and it's only this size right here. The lithium fluoride lenses that Webb uses have to be absolutely perfectly grown. So to be optically useful, it needs to be completely clear, unlike my homegrown little crystal over here, and be molecularly consistent. That means that the structure of the molecules are absolutely the same everywhere. Then they have to be cut, and then they have to be polished. Considering what these lenses will do, they are sure worth their weight in salt. We all know that black things get hot. Just take a look at these 2 identical cars. They're made out of the same materials, and yet the black one is going to be a lot hotter than the white one. And that is because it is absorbing a lot of those beautiful sun rays.
Now, the James Webb Space Telescope has 2 important sides, a hot side and a cool side. The sunshield blocks the heat from one side, and the mirrors observe on the cool side. It even has a radiator to keep it extra cool. But everything except the mirrors are black on the side that needs to be cool.
So I was questioning, why are Webb's radiators coated in this super dark paint? Now this paint is made by Ball Aerospace, and it's called Ball Infrared Black, or BIRB.
And it somehow is vital to regulating Webb's temperature. So the reason temperature control is so important on this telescope is that the telescope observes in the infrared spectrum of light. Now, we may not be able to see infrared light, but we do perceive it as heat.
And so to get data without any interference from Webb's instruments, they have to be cooled. I am so ready for this. To well below 400 degrees Fahrenheit. So Webb's instruments naturally create heat as they work. And so the radiator radiates that heat out of it. I'm gonna take a look and show you around here. So I've got a flashlight here that we use for inspections. And if you look at it, this shiny thing over here, and then look how black that is. What? So why
are these radiators black? Well, as it turns out, things that absorb heat also emit heat well.
The reason black objects absorb and emit heat well involves a lot of math and a thing called the Stefan-Boltzmann law. But what it comes down to is the fact that they are highly emissive. Emissivity is a measure of how well something radiates heat. And according to physics, an ideal radiator is an ideal absorber. So I left this board outside for about an hour, and the side with the black paint absorbed a lot more solar radiation. And then I went back at night. The black side of the wood is cooler than the side with the white paint. It was acting like a small radiator. So it released its energy from earlier in the day more efficiently than the side with the white paint. The more emissive a material, the more it can transfer heat. And the ball infrared black paint on Webb's radiators happens to be one of the most emissive substances ever sent to space.
Opportunities are endless. What if you had the ultimate tool to kickstart your dreams? Introducing Global Domains International's $10 per month comprehensive digital package. The ultimate starter kit for your online venture. With your own .ws domain name, you get a unique and credible online identity. Stand out in the crowded digital landscape with a fresh, memorable address. Site Builder Plus offers you the power to create a stunning website effortlessly. Choose from over 100 professional templates, use the intuitive drag-and-drop editor, and enhance your site with free stock images and a dynamic photo gallery. With up to 10 personalized email accounts and easy access from anywhere, stay connected and professional with GDI's web email features. Take advantage of the world's leading blogging platform, WordPress, with GDI's enhanced hosting services. Enjoy 10 GB of storage for use on multiple blogs. Reaching your audience with ease. Share your online presence in one convenient place with clicks.ws, making it easy for your audience to find and follow you. For the experienced user, our basic hosting and URL forwarding services offer complete control and flexibility for your custom website. Ensure your website's security with free SSL certificates, boosting your credibility and search engine rankings while protecting your visitors. Join our global affiliate program and earn with our 5-layer compensation structure. Enjoy additional bonuses and rewards as you grow with GDI. Empower your entrepreneurial journey with Global Domains International. For just $10 a month, transform your ideas into reality with the ultimate starter kit.